Let's take a look at finding the capacitance for something that's not a parallel plate capacitor. I know that the capacitance is the charge over delta V. That does not change. And so this particular instance we're going to deal with here is the spherical capacitor. I have a conductor right here with some positive charge. Doesn't matter if it's solid or hollow because it'll all be on the outer surface. And then I have a negative charge on this one right here. The charges still need to be of opposite signs and equal in magnitude but opposite in signs. And the trick is trying to figure out what delta V is. Now let's come up with a few constants. First off, these are spheres, even though these look like they've been out in the sun a little bit. But the radius of this one here, we're just going to call A, and the radius of this one we're going to call B. I know that the voltage is equal to the negative integral of E dot dr from some R initial to some R final. In this region right here, I'm basically integrating from this surface to that surface. The electric field at any point in there is due completely to this positive Q right here, not to the negative Q, because I'm inside that shell. And so my electric field is going to be equal to the electrostatic constant times Q over R squared R hat. Since I'm integrating from here to here, I'm traveling the path from the positive to the negative, from my initial to my final, that I'm going in the same direction as my electric field. These two are in the same direction, and therefore this just becomes negative E dr from A to B, which is negative integral K sub E Q over R squared dr from A to B. K, E, Q are constants, so we can pull those out. So this is equal to negative K, E, Q integral from A to B of R to the negative 2 dr, which is negative K, E, Q times negative 1 over R from A to B. The negatives will cancel out, and so my voltage here is K, E, Q, the negatives cancel, I think I just said that, times 1 over B minus 1 over A, which we can now put into the whatever form we particularly like. Let's get a common denominator to get our fraction going here. So this becomes K, E, Q, A minus B over AB. And since capacitance is Q over delta V, and this is delta V, well, I need to get this over on this side and these on the other side. And so what I end up with here is AB over A minus B over K sub E over Coulomb's constant, or the electrostatic constant. Or putting it in more sophisticated terms, this would become 4 pi epsilon sub naught AB over A minus B. And that is the capacitance of a spherical capacitor.